Yeah, so why not try and build a chip that's just inherently random?
Meet Thomas Ahle. I caught up with him in Zurich, and he's one of these rare galaxy brain people who's comfortable in probabilistic machine learning, formal verification, and chip design. However, there's a small problem. When the token god hands you something that looks like it works, how do you know it's actually right?
So my background is in theoretical computer science. I used to do algorithms for high-dimensional data, locality-sensitive hashing. Then I moved to normal computing to develop thermal computing, also to speed up Bayesian intelligence. Sometimes I think about it as the Lovable for chip design. So we take it all the way from your intent through the design, through optimizing your design, to formalizing and verifying your design, all the way to tape out.
Now, I didn't fully appreciate this before. These days, a chip doesn't necessarily start in a factory. It can start as code. So engineers design the whole circuit in a language called Verilog, almost written like software, and only much later does any of it become physical silicon. But first, that code has to be simulated and formally verified. It has to be proven correct. Because once a chip is fabricated, if there are any bugs, you're in big trouble. So a few months ago, Thomas blogged about building a Verilog simulator using a swarm of AI agents collaborating with each other, and it generated over 500,000 lines of code in 43 days. Now, the reason he needed to do this is that commercial software costs a ridiculous amount of money and isn't very friendly to using agents. $10,000 per seat or something.
Yeah, for one CPU kernel.
If an AI can generate a chip design or a proof or a working program, how do you know it's actually correct?
The percentage of tests that it got right, or like even like the Fable, it was like, oh yeah, it got like 70, 80% tests correct. And it's like, yeah, but I talked with the people who made the benchmark and like, yeah, but did it get any of them actually right, you know? Like.
Now in chip design, noise is the enemy. Manufacturers spend a fortune getting rid of it, but in thermodynamic computing, the opposite is kind of true. The noise is the computation. It comes straight out of probabilistic machine learning, which already runs on randomness and uncertainty, and thermodynamic computing tries to make the chip itself a stochastic differential equation. Let the chip's own noise settle into place, and then it can land on answers that would normally cost a fortune to compute.
And then you infuse all of this noise, and it'll start to behave according to these stochastic differential equations. It actually behaves sort of according to the inverse of that matrix.
They've already released their first version of this technology. It's a chip called CN101, all the way to silicon. It's still early days, and it's aimed at a fairly narrow band of probabilistic workloads. But the real test is, what can the benchmarks say once they scale this up? And something of huge interest to us at MLST is, if we're going to let AI build everything, what kind of understanding do we actually keep in the overall process?
It's not just that it's getting smarter, it's also that humans are getting dumber.
Now, I should disclose that Normal Computing very kindly offered to cover our production and travel costs for this show, but we kept full editorial control.
These are tools for device manufacturing. It's things like, it's compilers for RTL. It's like where RTL is like the programming languages you use. So if you're building a new chip, you typically don't draw all the different gates and so on. You write it in programming language like Verilog, which has sort of constructs that are it's like a super parallel programming language, which have a lot of constructs that map well to hardware. But then there are actually no good open source compilers for this system. So the whole hardware industry, it doesn't have the same open source feeling as like software, where all the good stuff is free and there's like this big vibrant market of tools here. It's much more locked down to like big providers. But people then, they compile this too, and they get like a netlist. They can start building their schematics. They can also look at it. You get like these giant things that you can eventually send to the fab. But they also need to do simulations, for example, for testing. You can do like formal verification.
Let me just play that back so I understand it. So Verilog, it's a bit like a programming language for describing a circuit. And what we might probably, before we go and get that fabricated, is we want to do simulations because it's very expensive to get it fabricated. So yeah, we can design this circuit and do simulations.
Yeah, exactly. It's super expensive too. it could cost you what they said. Like there was this famous Intel division bug in the 90s that probably cost them between $500 million and $2 billion. And I mean, that's a lot of money in the 90s.
Yeah.
I think there are other examples later on that nearly bankrupted some of these companies, like tiny bugs that managed to make it through to the fab. And it's a really different world again from software, where we just if people fix stuff in prod, you just move fast and break things. It's definitely like, yeah, people are much more paranoid in the hardware industry, which is also why it's a cool place for formal verification, formal methods to thrive.
Okay, so you're saying at the moment there are these commercial, verifiers and simulators, and they cost a ridiculous amount of money. So is it something like $10,000 per seat or something?
Yeah, for one CPU kernel. Right.
Dollars.
Yeah, like say you want to scale this up in a data center with 1 million agents running, like you're gonna I mean, compute is already expensive, but not that expensive. What is that? $10 billion or something, right? Just for those licenses. And I think actually that's one of the reasons also why AI still is not as popular in the hardware space, because they haven't been able to train, like the models are not as trained to this kind of workloads, because they just it's not feasible. Like you don't have all of the open source code out there to start the training, but you also don't have the tools that they need to learn to use. You don't have the all of the the tasks. Like you can't just all of the reinforcement learning on top of it. I mean they clearly are doing some of that. Like we can also see from model generation to model generation that they are getting better, but it's kind of day and night between like Python or JavaScript. We've been sort of developing these EDA tools in-house using AI, I think I probably have the world records of the longest running agents, having like some 20 GPT agents running for around 6 months now, still making progress.
So as I understand correctly, so similarly to, Anthropic, Carlini had this blog post out, and, they had a functional specification of a C compiler, and they had about 40,000 agents, and they reproduced a C compiler. You did a similar thing for an EDA.
By the way, right? So.
Well, I mean, that's an interesting thing as well, because this is what I want to get to, right? That it's tantalizing that there are some domains that are so well evolved that we have, they might be very complex, but we have a functional specification and it's reasonably coherent. So the idea is we get a shitload of agents and we reproduce the function of this software based on these tests, and we do it recursively, agentically, and so on. Now, my contention with this is I think that it's not about where you end up. It's not about the functions and the tests passing. It's about how you got there and how structured it is. Yeah. So there is this tendency with agentic coding to build a spaghetti monster, which seems to work, but because if you think about it, in this project you're talking about, I think you said there's like 500,000 lines of code. Yeah. And in 5 years' time, there's all of this code that probably, you folks haven't read most of it. That sounds like a problem.
Yeah, I think for a lot of this stuff, we're relying on the hope of some kind of escape velocity from code complexity, that the models are going to keep improving faster than our code gets messed up. I had those 3 days of Fable access, and it was pretty good. Like it definitely cleaned up a few things that GPT-5.5 had messed up.
But did it though? Do you think it could be deceptive? Because when Fable comes out, all of a sudden 4.8 looks terrible, and when 4.8 came out, it looked amazing compared to 4.6. So there's something deceptive about it. A bit, it's like a parlor trick.
Yeah, no, it's true. Like in principle, it could all be smoke and mirrors. I mean, but I think that's why it's good to have also the hard tests, right? So I could also see that it was actually suddenly I was making more progress on the more objective tests than I hadn't seen for a while. Yeah. With the other models. So I guess that gives me some trust But it is weird to sort of not have the same in-depth level of understanding everything in your code and definitely miss it.
And I'm interested in what the consequences of that are, because you said you put this blog post out earlier in the year, and then when we had a chat on the phone, you said that you noticed there were some things that were wrong. Yeah. And there's this tendency though to accumulate understanding debt, and when that happens, I think from an evolutionary point of view, you're stuck, because I think deep grounded understanding of how things are the basis for the next design decisions, the next evolution. So do you get into this kind of fishbowl thing where like now you're in no man's land and you don't really know what to do?
Yeah, I do think it's important to understand as much as you can and have time for. I mean, I think for compilers, there is some very important architectural design decisions. And then there's a lot of sort of just implement like these like 100 different functions, like they all just especially like modern compilers, it's like layer by layer by layer. You have to lower these things from like the front end level to the middle interpretation to the back end layer, and a lot of that like you definitely don't want to have to write. Like it also parallelizes as well, I think. I mean, I'm sure it could be one of the reasons why Anthropic also picked it. We talk about this ProgramBench thing, I think Facebook released, where it's a benchmark where the task, I think they took 150, 170 programs. Some of them are really complicated, like FFmpeg is one of them. The AI just has to re-implement them without internet access. Yeah, basically when it came out, they had like, all of the LLMs got 0% because none of them like were able to pass all of the tests. But I've seen like people, like I very rarely see that when people post benchmarks for this thing, they always post this like, oh, the percentage of tests that it got right, or like even like the Fable, it was like, oh, yeah, it got like 70, 80% tests correct. And it's like, yeah, but I talked with the people who made the benchmark and like, yeah, but did it get any of them actually right? Like did it, because it's if the program only passes 70% of the tests, it's probably not right.
I know, and in a way, this is the thread that we were talking about before. Like for the last 60 years, going back to behaviorism, there's been this kind of thread between structure and competence and prediction, right? So essentially, this ProgramBench is making the argument that you can learn the physiognomy of a program from its external behavior. So you can learn the deep structure, the constraints, and so on. And I suspect that is not possible, unless, of course, the LLM already knows about the source code because it's in its training data or whatever. But what do you think about that?
Yeah, I think humans do it all the time, actually. I think there's the whole field of kind of reverse engineering where people, actually, I listened to something with the FFmpeg people where they were talking about all these codexes that they put in there, and they like a lot of time they have no idea what they do. Like it's just like this obscure blob of code. Like they probably don't even have access to the code. They just have a couple of like video examples that were encoded with this, and maybe some people had shared some screenshots like with clips from the movie, and then they had to go and try and read this like encoded blob and being like, what is it doing? Like, how could we like write a program that decodes this thing? And somehow people are able to do it. We must have some sort of prior, right? Like what are the typical things people put in a video codex? Like, oh, there's probably some, Fourier transforms of some stuff, or they're probably like you chunk things up, or I don't know. I haven't done that much video encoding, but just like completely black box, just try and keep improving your program and visualize the output until the end a movie comes out and you have an idea of, oh, this probably looks how the movie is supposed to look. And
yeah. Well, that's an interesting thing as well. So we can hill climb in a partial knowledge regime, right? So we might have a verifier. And as you say, like a lot of science is a form of intelligence where you're using MATLAB and you do like a Laplacian, or you do an image plot, you take a distribution and it takes shape one step at a time. So what you're doing is you're taking steps into the unknown, and it's like there's a generation discrimination asymmetry, right? So we can discriminate well, but we can't generate yet, but we take these steps, and then when we get there, we now kind of collapse that into a model, and then that's the artifact of the intelligence.
Right. It's like a star search or something where you kind of you prune your search tree as you go, and like what seems most successful so far. Like
Exactly. But to your point, every single step of the way, we're using the toolbox. So, you know, there are some folks that are really good at riddles or intelligence tests, and a lot of it is skill, right? Because they have a toolbox of abstract tricks that they use. But then there's this question of, well, maybe that's all it is. Maybe there are these natural patterns, these abstractions that we can compose together and handle any kind of novelty in the intelligence setting. Yeah. So therefore, maybe language models could do this autonomously. I think they possibly could. Yeah.
This is a good point, like, because I tried to get an answer, I think, from Noam Brown at some point on Twitter about this, because you see how the better a pre-trained model you start with, and then they start reinforcement learning on it, and it seems like it gets up to some, like the reinforcement learning works better and better depending on how good the model was to begin with, in a sense.
Yeah, it's super interesting. I mean, I agree with you. I think it's wrong to say that LLMs are not intelligent, right? Because there is some kind of a combinational closure. And that means from the primitives in an LLM, we can do hill climbing and we can build some computational structure to solve problems. But that's not quite it. And it can happen at different levels of abstraction. So if the LLMs have higher abstractions, then they can, you know, traverse the combinational closure of the higher abstractions and they can solve the problem. What seems to happen, though, is, I mean, there's no continual learning, so those don't get, you know, added to a library and reused later. But there's also no abstraction. So what humans would do is they would look at this computational graph and they would say, I see that that's just an analog of this thing over here. And I'm now going to compress it into a new variable that screens off all of that complexity. Why do language models not do that?
I think you're getting into like continual learning type thing, which is obviously a thing we lack. I do think language models do that during pre-training. I do think like that's why, for example, Mythos is so good at doing stuff in our code bases, is because it has somehow seen a lot of code, and it just seems to have this sort of intuition for bugs and problems and so on, and that must be, you know, kind of like that. You know, it's seen the patterns before, it has some kind of abstraction. But it's true, like when you actually are doing sort of running them more live, they don't do it very well. Like they don't, and I think a lot of people these days are thinking about this. How can we do better continual learning so it can just build all of these abstractions and these things really well on the fly? I mean, I know some companies are actively against trying to do that also.
Why?
Like, I think Anthropic, right? I think Dario said like he considers it like a big safety issue too, because you could easily lose all of the work that has gone into alignment if the agent is learning too much on the fly. Then it gets further and further away from the sort of safe checkpoint. But I think there are enough other people working on it that it'll probably happen. But it's definitely like a big unknown, right? And I think it'll also have to change a lot of things in how we serve models, for example, because suddenly you need to be able, like if we mean by continual learning that we actually update the weights live, it causes a lot of problems for the current paradigm, because then suddenly you can't use the same weights for all customers too. I mean, I guess thinking machines has this thing where they have one shared model and then like some lorers on top. So maybe something like that can work, but it's still like you have to somehow, keep doing this all the time. And so we're also working in normal computing on like alternative forms of computation, like these thermodynamic chips, or just sort of unconventional computing. It actually becomes sometimes hard to keep the memories in these analog resistors unless you keep learning at the same time as you're doing inference. Like you have to use these fancy substrate like memristors or something if they have to be permanent. But if you're just using like sort of basic capacitors like you have in DRAM or something, they require constant refreshing. So either you just have to spend a lot of energy on that, or you just want to keep the learning going forever. That way they kind of automatically refresh. And that's probably more similar to also how brains work, right? Like they never like just, I don't know.
The same.
What Chomsky or somebody would say, but if they were just freezes. I think like the synapses and stuff, they're always adapting.
Yes, exactly. I think out of all of the words we can use to analogize intelligence, adaptivity is the number one. And in a sense, when we look at Claude, you can look at, is Claude the model? Is it the ecosystem? I think it's the ecosystem, right? So it is adaptive because...
Say it's the personality or the persona or something.
Well, there's a tendency to anthropomorphize it, but no, like millions of people are using Claude Code because this is tangentially related to how we come up with causal abstractions in the world. So, the way we do it is we are in the world and we are agents and we can make decisions and we can reconcile uncertainty and we can say what would have happened if I did this, and I can share it with my friends, and there's this wonderful percolation process where the abstraction has just become embedded. Now, that does happen with Claude Code, right? Because there are people using it on their machines, they're actually running tests, they're doing counterfactuals, and then all of this gets retrained in the next version of Claude, and then someone else will reuse that abstraction. So we have the adaptivity as a system.
Like this shared brain, where all of the experiences go, what's called the Borg or something, go back off, and then,
Yeah, so, but it's interesting to make, to discuss, is that effectively the same? Like if we actually had some hypothetical real-time adaptive divergent Claude, would it be much better than the Claude that we already have? And it's also related to the work that you guys do, because, the process of intelligence in my view is the creation of these coarse grainings, skills. And that's kind of like what you guys are doing with ASIC. So you're building this customized hardware for making certain types of computation go really, really quickly. And it's almost like that's the result of intelligence. So you say, I'm going to take a very, very complicated thing and I'm going to whittle it down and represent it in the best way I can. And then I'm going to bake it into a non-adaptable hardware substrate. Is that fair?
I think that is what we're working on right now, is this idea of trying to build hardware that best fits like the models we have right now, and just like really make a super efficient inference. You could say like in the past, at least, the issue has been you stop yourself from innovating on the software side if you lock down your hardware too much, right? Like the NVIDIA chips has been pretty good for innovation. Like they're pretty flexible. Of course, they also have guided the way we do AI in a lot of ways, like towards matrix multiplications and so on. But still, people have been able to innovate. But on the other hand, I think also hardware is getting easier and easier to make with these kind of AI for EDA tools. So it's sort of shortening like maybe now people are thinking about like making their CUDA kernels, right? It's it's not so unreasonable to think that soon we'll just be doing our AI for making, like, instead of CUDA kernels, we'll just like make some custom circuits for every single thing we want. So if you come up with if you want your new algorithm to run really fast, you just design like a specialized circuit for that. And the AI helps you like optimize it and check that it's correct. And of course, you still have the fab, but we're getting better at like batching things for the fab. But I mean, I also think having the really flexible hardware is going to be very interesting, like the stuff where it's learning on chip, and ideally like maybe the more adaptability that it has and the less we need to bake in. I don't know, it's just more cool, I think.
Yeah, but isn't that a wonderful example of this recursive self-improvement? Because as you say, like we're building the AI, and then the AI is helping us build better kernels, better software, better hardware, which then in turn makes the AI better, and then you get this kind of loop.
Science is a recursive self-improvement in a way, right?
Exactly. But we should bring this to life. So there's this concept called autoformalization. And you guys on your website, you say basically that you have done something similar to AlphaProof in respect of building chips. And roughly speaking, AlphaProof is when they won silver at the IMO in 2024. And what they did back then was they used a language model to generate a bunch of lean code. And then obviously it was a little bit messy, so some of the formalization was by hand, and they did multiple renditions and so on. And then they would do verification with lean. And you're kind of doing something like that for chips.
Yeah. It's interesting because there is the autoformalization, which we define as taking human specifications and writing up and turning them into formal specifications in lean, for example. But then of course you also need the proof step, where you provide prove that your code, whatever you have, actually satisfies that specification. And I think some companies like Axiom, for example, they're very focused on this part, right? Like and also in some sense, AlphaProof, that's also the main thing it did was it started with a formalization. And then the hard part was training the model to provide a proof or disproof. I think it's actually a really nice trick in AlphaProof was that when they did the formalization of the proof, it didn't really matter if they got it right or wrong, because if they just asked the model to provide a proof or a disproof. So if they got it wrong and it was no longer true, then it would just prove that it was not true, or like as you could still use it. Of course, like when they actually did the IMO challenges, they wanted the autoformalization to be correct. So then they did it by hand. But they didn't need it for the training, which I think helps scale it up. I think, yeah, so we can do a similar thing with hardware, by the way. It's pretty easy to just take some chip design and then, you can basically just come up with some properties that may and may not be true. And then you can train the model to try and prove or disprove that this thing holds. But that's all about creating the proof. But then the autoformalization, in some sense, it's harder because it's all like because it's harder to create the training data for it, right? Like I think that's kind of also a story about AI in the last 2 years since reinforcement learning. Like anything you can create good RL environment for, you can probably learn. But anything else is like out of reach right now. And so some of these chips have thousands of pages of specifications. And if you want to turn that, you're turning that into a formal model. It doesn't really, like if you got just a couple of words wrong somewhere or a couple of numbers, then it doesn't work. Or like then what you prove is not important or it's not relevant. And I think, it's always been an issue in the chip industry, like and they've kind of tried to solve it by having orthogonal teams. So they have one team that's designing the chip and one team that's designing the tests and another team that's designing kind of tests of the tests, like where they kind of like coverage. They call it functional coverage, where they measure what the test and then check everything off. And so hopefully, like if all of the three teams have read something the same way and understood it the same way, hopefully they have the right idea of it. You can try and do something similar with AI. You can argue whether it's really orthogonal if it's the same model that are doing each of the three jobs. I do think it is quite orthogonal. Like I do think there is enough entropy in these models when you do long runs. And you can definitely find a lot of bugs by just doing things many times and see if there is agreement between them. But it's something. But it's definitely like a trust exercise too, and a human exercise to figure out how do we get the hardware engineers to trust, and like how do we make it easy for them to verify that our formal model fits with what they thought, like, and you can come up with there's all kind of different tricks you can come up with, both to make it more visual, like what your understanding is and like whether it matches, and like ask questions and see if you agree with the questions, or show examples, or you can also try and do some kind of back and forth. I don't know, lots of tricks you can try, but it's an interesting problem, and I feel like no one, like the AlphaProof and all of these other people, they never really solved this because their math statement were just one paragraph. They were not like thousands of pages long.
Oh yes, yeah, interesting. Yeah, because with AlphaProof, I think they wanted to use Lean 4, and there was hardly any stuff for Lean 4, so they created a converter from Lean 3 to Lean 4, and they needed lots of human, people to fix it. But I guess my point is that they needed to fine tune a language model on a ridiculous amount of Lean code, and then they were using Lean as an intermediate. Interestingly, like with their new model that they won the gold on IMO, they weren't doing any verification at all, not in a formal sense. But then, is there a spectrum? Because the way you were just describing it, it's not like it's a binary, right? So you were talking about test coverage and different perspectives. The blind man and the elephant. So there are these functional tests and these descriptions, and we can do visual inspection and so on. So will it end up being a case where we're always wrestling with something we don't completely understand, but we're using as many signals as possible to get there?
Yeah, I think where we're going now is also trying to encompass more of the spec creation, right? Like obviously when we start out, people already have written down all of these specs, and we want to help them out with those. But when you do that, you also you miss out on the whole intent that got into and the whole process of creating the spec. You don't know, if there's just some numbers somewhere in there, you don't know why they chose those numbers and not some other numbers. And I think you sort of, by internalizing more of the process, at some point you can at least be as safe as any human could have been about this chip, right? And like there might also just be some ambiguity that no one cares about.
The ambiguity thing is interesting. There's a wonderful talk by Eric Curiel called "Math Does Not Represent," and he was talking about generalized relativity, and he was talking about four different completely orthogonal representations of that. And it was a similar thing actually with AlphaProof. So like how many ways are there in Lean to represent non-negative numbers? Apparently there's quite a few. And so the Google guys were just to stimulate the model, they were representing the problems in different ways. And is this? It seems like this is almost
they're training data in a way, like, right, if they autoformalize the same problem in different ways, they actually get different problems.
Yeah, both in terms of the intelligence, so how can we kind of bootstrap the model to do better intelligence, but also in terms of the legibility and abstraction of the final output. So I guess when people think of autoformalization, we have this almost, kind of idealist view that there is a one true representation and it's just going to be legible and everything. But it seems quite vague.
Yeah, it's a one true representation. No, I guess definitely there's not one true representation. With smaller chips, like say you have just like floating point or a crypto chip or something. I mean, the specification is actually pretty simple for those. It's more when you come up to like the big like system level stuff. I think software is in many ways ahead of hardware. I mean, in terms of formalization, they're behind, but in terms of thinking about these like architecturing together with AI, right? I think a lot of people now, they'll run their architecture documents by Claude or somebody and being like, hey, what do you think of this? Or should we move things around here? Or boom, boom, boom. And I think this whole discussion, like, it sort of helps the models understand like what your intents are and what you care about and what you don't care about.
And just to give us an example to bring it to life, there was that DRAM article you published earlier in the year. The article was talking about these timed Petri nets. And I did look this up on the internet. Apparently it's a thing from the 1960s for describing distributed systems. Explain that.
What we talked about before with the formalizations is very, it's like at the RTL level, at the very sort of cycle level where you care about, you want to prove that the exact thing happens at every single clock cycle. But of course, there is another kind of formal, and that's very important for things like adders or like arithmetic circuits or crypto. But a lot of the hard problems people have are more these, you can say, like kind of system problems, or more like protocol level stuff, like the things actually maybe also more popular in software has been like proving things like this system can never deadlock or live lock, or sort of like protocol level properties. And like all of the sort of timing requirements between different things make sense, and there's no internal inconsistencies. And there currently exists different formal languages for these things. Like for the cycle level stuff, people use these system Verilog assertions, SVA type things. For the higher level protocol things, there are more classic things like the TLA plus, I think by Valiant or Laporte or something. And yeah, so we try and formalize things in both ways because it can have different, it's useful for different things. It's possible at some point it can all merge if you supply. It's kind of like you're doing very high level math, and then you can reduce it all the way to the axioms if you want to. But I think it's also interesting. It's a very new field, so we're trying to explore it different ways. And these time Petri nets is one way to represent like these super parallel systems that you have, for example, in these memories where all these different banks, they can you can activate for example, if you activate one of these rows, you have to wait for the data to run down to the bottom before you can read it, for example. Then after a while, you have to refresh it because, again, it's like these capacitor DRAM cells. They have to be refreshed all the time. But you can also be working in a different memory bank. There might be lots of them on this chip at the same time. So there's certain but then there might be some circuitry that's shared between the banks. And so certain things that are like interbank dependencies and intrabank dependencies and also bank groups. And people build really crazy stuff actually in there.
Very cool, very cool. I mean, what's really exciting to me is that it's possible to build chips that can do certain types of things orders of magnitude faster. And that's why I want to talk a little bit about thermodynamic computing, right? So, so apparently, instead of forcing transistors to settle at 0 or 1, you let noise do a random walk and bias it. So the chip is a stochastic differential equation, right? I mean, that sounds crazy. Like, how does that work?
Yeah, I mean, this was one of the things that got me to Normal in the first place. Before before Normal, I was at Facebook, as we call them, in the research group that does probabilistic computing. Like we were doing like these Bayesian neural networks, where you assume like probability distributions over all your weights, and you try and infer like the posterior from like the prior data that you look at. But a lot of these techniques were kind of slow because you had to like either try and do lots and lots of repetitions with different random seeds, or you were trying to do it analytically. I mean, that kind of maybe takes a little bit of the point out of the probability. But then you could also but then it's funny because you have these chips, and like the chip manufacturers, they spend so much time like getting out every single little piece of noise out of their systems and like having these extremely sharp margins for everything, like so much, precision. It's probably like the most precise business in the world. And then what do we do with them? We just like add a lot randomness everywhere. So why not try and build a chip that's just inherently random? I think the brain probably has a bunch of randomness. But here, the first chip we made was then this, you have this array of capacitors, and you have certain resistances between them you can program. And then you infuse all of this noise, and it'll start to behave according to these stochastic differential equations. And then you think, okay, what can we do with that? It's a new computational paradigm that I've found very interesting to explore, where you can say one of the things, for example, you could do with it is it actually turns out that the matrix that you put onto the chip in the weights differential or the stochastic differential equation, it actually behaves sort of according to the inverse of that matrix. Yeah. And so then we could try and capture and average it out.
And when we spoke about this on the phone, you said something very interesting, because, we often talk a good game about this. I was talking with Michael Jordan the other day, and, we need uncertainty quantification, we need adaptive computation. And
I think this was kind of one of the issues we had, because I think Bayesian machine learning was really strong for a certain amount of time when, at a certain point in time before the generative AI, because you had the one output, and then it made sense to have this sort of distribution as the output. But now you have these sequences, as you're saying, you keep putting these tokens out, and I think no one really cares about what is the uncertainty about one particular token and having a better distribution on that. You really want to know, after the model have thought about 10 different options, and it's backtracked and all of this stuff, and it comes out with a final answer, what is how much can I trust this answer? You either have to go really deep on mechanistic interpretability to try and really carry all of the uncertainty all the way through that, or you have to try and use some more maybe anthropomorphic methods, I think, that are based on how would humans estimate their uncertainty, and and try and apply that at really high level. But and sad you lose some of that beautiful math in there.
Because it's actually really cool that you've got a Bayesian background, because the way I introspect about this is, when you have a thought and you have some intuitive notion of how confident you are, and it seems to be because you have a deep structure. So you can introspect and you can rationalize, and you can say, okay, well, there's this component and this component, and there are these constraints. I'm not quite sure about that bit. And that seems to be the missing link.
Yeah. We actually did some experiments back also when transformers first became popular, where we tried to do It's before we knew exactly what the company was going to do, that it was going to be AI for hardware. So we wanted to do like predictions, and we just sort of building Bayes law into the model. So for some particular question, it would try and find like lots of pieces of evidence, and then it would say, what is the probability that this, like, if the answer is yes, and if the answer is like different things, like what is the probability that I would see this evidence? And it would do that lots of times, and then at the end, you could use Bayes law to say, okay, then what is the probability that the original statement was true or false? It actually worked really well. Like we did this, I did some like internal like prediction game, and it beat everyone. We had multiple versions. One of the versions, it was more neurosymbolic, you could say, where you would just have the model come up with all of these probabilities, and then you would manually calculate it. And then I also tried another version where I just told the model, now use Bayes law and go do it or something, and somehow it actually did a little bit better. So I don't know how it did that, or maybe it just was able to. Maybe it's because it was able to look back and think, actually, a couple of these values I probably bullshitted, and I'll just ignore that. Or, it's interesting. I know there are some people training, like there are some benchmarks now for where people are trying to predict polymarket and this kind of stuff with LLMs, and they have benchmarks for that. But I'm not quite sure if they use these sort of techniques, or it's all just end-to-end reinforcement learning, and they hope it just picks up good methodology by itself.
But it's a wonderful example of this kind of adaptivity specialization loop. Yeah. So, for the first, and this is a common with vibe coding, so for the first month, there was a false positive every single day. Yeah. And, so I just created a skill, and then Claude would just retrain it, and then eventually it just kind of converges. And this is the bull case of vibe coding, right? That, like you just, every single day you fix it, and eventually you'll come into the landing track. And it works really well. But in a way, this is similar to what you guys are doing, right? Because you have this kind of outer loop, which takes something complex, and then you kind of compress it, and you optimize it, and then you bake it into a kind of crystallized hardware.
Yeah, I was thinking about, there is this older tweet by Elon Musk. I don't know if people were laughing at him. I mean, I don't know. He tweets a lot, but he was saying like, why don't LLMs just write the binaries directly, or the assembly?
Oh yeah, I saw that. Yeah.
I don't see why we wouldn't be able to do it. It's a question of if we would want to do it, or like do we think, because like I think there's some fundamental computational problems always, in like everywhere in the world. We don't always, like, recent years we don't focus so much on them because we're so excited by AI, and we want to we're just interested in all the stuff that AI can do really well. But I mean, obviously things like cryptography, or like some of these like basic algorithms, like you never want the LLM to just do it, even if they can do very large number multiplications. It's just super inefficient. Or like you might as well optimize like a circuit or a piece of code for that. And compilation has some of the same problems where you want to and chip synthesis, where you're trying to explore all these different designs and so on. So you don't necessarily want to have the LLM do it because it's so slow versus some super optimized loop. Not to jump too much in things, but it's interesting to think about chess again. Like, of course, you had like the AlphaGo thing where it was like everything ran through a neural network, right? But today, the state of the art is in like Stockfish, of course, is that they did more like hybrid. So they took the neural networks and they made these like a certain type of neural network that can update really fast when you change the state, and then they combine it with like just super fast search, and it actually outperforms the best like open source like AlphaGo type chess engines.
Oh, really? Using like adaptive fine tuning and structured inference.
I don't know if you call it adaptive. It's more like they took the classic chess search engine and they replaced the evaluation function with a neural net, but like kind of a very shallow, wide neural net that they can that is really, really fast to evaluate. And yeah, I think it could be that for something like synthesis and compilation, there's a similar thing where it's like you could try and do it all with LLMs, but at some point the speed is a bottleneck, and like you can you get a benefit from having more knowledge and more intuition and all of this stuff, but at some point there's also just a hard computation problem where you just want to brute force some stuff. Yeah. And at that point you want to be able to switch to like more classical algorithm.
Absolutely. Now, before we were talking about thermocomputing, and so you folks have done some work that is incredibly, like, it has huge potential for things like Markov chain Monte Carlo, I think, and diffusion models. But you did say to me when we spoke last time that in some cases it can be a false economy. Like, for example, you could have a diffusion model which might have like a different type of neural network on the end of it, and you might find that the benefit that you have doing the diffusion might be bottlenecked by another part of the model. So in practice, where can we see a huge uplift?
I think it's always interesting when you build hardware, because there's always this co-design problem with the algorithms, right? The algorithms are so based around the GPUs and the hardware we have now, and so you can try and target some of those bottlenecks. Like you can make hardware, like we talked about with the thermo DRAM, that's super efficient for the memory. Like that might speed up inference, but it can only speed it up, like say there's some like 10% GPU utilization now for inference. Like you can hope to have like a 10x there, but you don't know if you suddenly have access to that much, like that different architecture, what like new algorithms could you build, like if you really went all in on that. And that's some similar thing with the diffusion stuff, right? It's like now the architecture is not that efficient in terms of like randomness, like the GPUs. It's kind of people don't really want to sample like tons of Gaussian random variables everywhere, and so they maybe also build architectures where they sort of try to remove that bottleneck by not focusing too much on these things, and then they instead so we can build new hardware that makes that more efficient and that has some performance gain. But to really make the most of it, you then also have to come up with the new models that sort of go all in on that. It's interesting, these Notion and apps. Have you thought about this? How all of the apps now, they want to be like your central AI. Like Notion has this, they want to integrate with the other apps, and your Linear have an AI and they want to integrate with the other apps, and like everyone is trying to like capture like being your central AI assistant, and then all the other apps will just be tool calls.
I know. I have to be careful because Notion are now sponsoring some ads, but no, they. I actually use it a lot because it's got an amazing agentic interface. It's got like a CLI interface, so I use it from Claude. But what they want you to do is to pay them to use the agents that are built in at API prices, and I don't really see the reason in doing that when I've just got a Notion MCP, I've got a Notion CLI.
API prices stuff is really killing innovation, I think, in that space, right? I mean, I think Codex, I think they are actually opening up more that you can use your accounts. I saw just yesterday, I think maybe also Anthropic opened up some that you could use some more, like the SDK you can use with your accounts. But it's just like the price difference is so big that if you have to use API pricing, like nothing is competitive.
Well, I mean, we don't have to go too deep into this, but I think creativity is all about respecting constraints. And I mean, you studied linguistics at Oxford, and Chomsky always says that there's a difference between linguistic competence and linguistic performance. So, he's using this bulldozer analogy for ages. He said that I love bulldozers too. They're great for clearing the snow. They're not a contribution to science. And he even said about Deep Blue that a computer winning at Deep Blue in the way it did is a little bit like a bulldozer winning the weightlifting competition at the Olympics.
I think it was in a way, like with Deep Blue. I mean, now maybe modern chess AI is a bit more, it's a bit different. I actually worked on chess engines for 15 years. But I remember him saying that too, and I was like a bit surprised, because you'd think that if if your science is biology or you want to understand how humans do language, sure, like then maybe the LLMs is kind of not so relevant how they learn language. But if your science is more the abstract of what is language, I thought you would be really interested in seeing like different systems developing language, and you can comparing and see what's common, what's the same, what's different, and so on. That would give you like a wider understanding of what is the concept of this thing. I mean, of course, you have to have some kind of respect for AI language to even like include it. If you just think it's like completely, just some, I don't know, stochastic parrot thing, maybe you're like, I don't really care about it. I want to include it in my model of language. But if you do think it's actually doing language, then I think it doesn't really matter if it does it the same way as humans or not. Maybe it's more interesting if it's in a different way.
I know. You mentioned chain of thought, by the way. How much can we read into chain of thought? Right, because like some people just call it chain of thoughtlessness, like Sabaro, Kamahati, but actually it is probably the modus operandi now for doing interpretability, right? For actually understanding what they're thinking. Yeah. But you could argue that chain of thought is like the press secretary, not the orchestrator. So it's almost a post hoc confabulation. But that's not quite right, is it? Because that sounds a little bit like there's no causal link between the chain of thought and what the language model outputs. That's not true. So how much can we read into it?
Yeah, it's like you want to give the model somewhere to think, right? Like, when you do reinforcement learning, I mean, the chain of thought before the reinforcement learning and after reinforcement learning, I think it's very different, because before it was kind of, you try and prompt it and some tricks, they kind of work and kind of doesn't work. But once you do the reinforcement learning, you need it's like a Turing machine, right? Like it needs to have infinite memory and being able to have something to operate on. Whereas when you just had the transformer and just like single shot output, it's like, I mean, probably in the Chomsky hierarchy, it would be a completely different type of system, like, I don't know, an automata or something, right? There's like only finite amount of computation it can do, but now it can do as much computation as it wants. And it just has to learn to figure out how to do it. Like you could imagine building a really simple LLM type system, and with access to chain of thought, it would be a universal Turing machine. So now at that point, it's just no, because it can have this tape and it can keep reading and putting. I think that would be pretty easy to make a structure like that. But then the question is whether it can learn it. But at least now it has the like representation capacity, so it can do it, and clearly something is improving and working.
This is actually the bigger problem, like with the ecosystem, which is that software was always designed to be a thing that reduces complexity and introduces canalization. So spreadsheets, they're a great example of this. So now, accountants use spreadsheets, and financial, like everyone's using spreadsheets, and it creates an interface that everyone uses, and it reduces complexity in the system. This agentic AI, it just creates spaghetti everywhere. And this is part of the reason why people aren't shipping, because, it creates ephemeral, complex. It's a little bit like bash scripting on steroids. So I've now created this web that only I understand, and it's becoming more and more specialized over time, so I can't share it with other people. And the entire ecosystem is becoming very messy.
Yeah, no, I definitely think a lot of things are breaking now because of that. I mean, a lot of the open source stuff is like everyone just also like writes new code from scratch instead of trying to come together and hone these like shared libraries. But I mean, it is just for a lot of things more efficient than also going through, and you can get everything just the way you want it. But yeah, and I actually think it's very interesting when you're talking about with the spreadsheets and like this channeling, right? Because there's a lot of kind of domain knowledge inside of these tools. And that's actually also what I think people might be worried about who build these tools, like how easy like it is to kind of extract that knowledge, and like people building clones and so on of their tools. Like if you have like everyone these days are like locking down all of the data, right? Because they're realizing data is becoming so valuable. They want to keep it themselves or build something themselves rather than have other people use it. And I think it could be a similar thing with a lot of like specialized tools, because the tools basically are data, like they're developed over so much time, like finding all the right patterns, everything is built in there. So how do you avoid other people from going in and sort of, agentically extracting, distilling it, kind of.
I'm sure this has happened to you. Random people on the internet will like say, I've just generated this paper, I've just generated this code, have a look at it. And, there's massive amounts of AI psychosis out there, which is that like you do things that are slightly outside your domain of expertise, and Claude will convince you that, your stuff is not mediocre, it's great. And then you share it with other people, and other people immediately see through it. And this is a bit of a serious problem as well, in my opinion, because, I think there are experts experts out there who have really, really clear ideas about things. They've been doing software engineering and, they've been in science. And when they use Claude, it's brilliant if they're diligent, right? Because they can actually use good abstractions and representations. But there's now a tsunami of pollution out there.
Yeah, I don't... and it breaks this social contract, right? Like in the past, if I wrote something and asked you to read it, you could at least have assumed that I would have spent 10 times more times writing it than you reading it. But now you're really skeptical about anything, because like, why would I want to spend time reading some stuff that you didn't even read yourself, maybe? But a lot of this is like social problems, right? Like, how do we protect also the open source ecosystem from AI generated PRs where like no one has ever read them, and then these like volunteer maintainers have to like read through all the slop.
Yep.
It's not really fun. Have you talked with anyone about that? Like, people talking about like we need like a GitHub like a social credit system, like a karma system, so people can like downrate you, and like if you don't have high enough karma, maybe they'll just not read your PRs. Or
we do need that. Yeah. And Archive recently put gates on people uploading things there as well.
Right. Yeah, and they had this ban. It's like a 1-year ban if you have an hallucinated a citation.
Yeah.
But it's sad in a way, because it makes it harder, especially for new people and like young people to break in to that stuff, like, because then they don't have any karma or anything to show.
I know, but I think the broad reason we have this problem is that this technology is the most deceptive thing ever created in human history, right? And it's a serious problem, because it's all about epistemic subjectivity, which is that you generate things that you don't understand, and it convinces you that it's correct, and you can't see the glitches. And obviously an expert can look at it and see the glitches straight away, and it creates dependency. When you start posting stuff that you don't understand, you want to be consistent, right? You've now made a statement that I know about this thing, so I'm going to keep doing it. And then weirdly, people are very defensive about it as well, because if you criticize work that they've done with Claude, they take it personally. So it just creates this perpetuating cycle.
Yeah, and it creates a feeling of understanding that you might not actually have, right? And it's like, I don't know, doing an exam or copying somebody else's work. Like, you might feel like you wrote it, but you don't, like, your brain didn't go through the motions. And yeah, I think it's dangerous also for, like, if you're worried about sort of AI taking over, because it's not just that it's getting smarter, it's also that humans are getting dumber. Like, we no longer know, and like we get lazy in terms of understanding stuff. We don't read the papers, you just put them in AI and be like, oh, explain this paper to me or something. But yeah, it's strange, right? Because on the other hand, I mean, it can be like this big level, like speed, like it can speed you up so much, so it's like it's hard to not use it. But like finding out when you should stop and when you should start using it again.
I know, I mean, it's reminiscent of the Elon Musk tweet. He said there are no researchers at Tesla, there's only engineers. And this for me is the big problem, actually. It's a paradox, because you can use language models to increase your knowledge. That's a fact, right? If the purpose is to increase your knowledge, then, if you're a curious person, you can just dig and you can learn a hell of a lot. So why is it the case that on average they erode our knowledge? And I think it's Elon's fault, not his fault, but he says that engineering is like, this is a means to an end. So we are building this thing and it needs to pass these tests. And in a sense, I don't care if your knowledge erodes during the process, because that's not what I'm measuring you on. And, we shouldn't be binary about it, because clearly engineers, they trip up on things and they learn a lot along the way. But it seems to be quite convergent. Like when you're pursuing knowledge for its own purpose, you seem to you seem to build deeper foundations and discover new things.
Yeah, and I guess that's like a tension with like in capitalism or something, that the companies they're not trying to necessarily develop their employees. I mean, maybe if they can see a profit motive in it, but at the end of the day, they just want to get the job done. Yeah, and like, of course, if you spend a lot of energy developing your employees and then they leave and stuff, it's always a bit tough there. I don't know if there's a way to force it. But I think it's also a little bit self-inflicted because, I mean, learning stuff is just hard and like it can be like frustrating and it doesn't always get you in the same kind of flow as just prompting or something, right? And it's like, I think, yeah, I've been trying to use this. I think it was Kapathi who suggested this, like when he was learning some new stuff from LLMs, he didn't like copy paste it, or he would have like side-by-side windows, but he would always like write all of the code by hand. I made a internal app to try and, because we hire a lot of AI engineers, like it's hard to find people who are both like really good hardware engineers, really good AI engineers, and also software engineers. Of course, you have to be that. So we have to skill up people. We have to skill up hardware people and AI. We have to skill up AI people and hardware. So I made like internal like training tools and so on, where I try to have the same like blocks in there. If you like try and block, copy and paste, and at least like give people a warning and saying like you should maybe try and type it yourself. Like somehow it, like, you know, you wouldn't think so, but like it doesn't feel like anything. Like if I'm just looking at it and typing myself, like why would I learn it better? But it's just empirical that somehow like our neurons and stuff, like it's important like to go through the movements. You have to figure out what projects you need to understand in depth and which ones you're just making like where it doesn't matter as much. I think we get tempted with the AI to just start way more projects in parallel, right? Because like, oh, I can just start another one, and while it's working on that, I'll start another one. Yeah. And then suddenly you're like, well, there's obviously no way I could actually understand all of these in depth because now I started so many projects. So then you have to to stop yourself and being like, maybe instead of starting the 5th project, I'll go back and try and understand what's actually going on in the first couple of projects. I think maybe there'll be some evolution, like we're still learning all the social stuff around using these tools and what is effective and what's not effective. Hopefully and maybe we can even build some stuff into the tools. Is that what you're saying also with the scoping, like to try and make them better? And it's hard. I mean, another really hard social problem I think right now is how do you do teamwork? Like that's something I also think about as a manager. Like if everyone on my team is like staring at their 10 agents or something working on some stuff, when are they going to go and talk to their colleagues about this stuff? Or like if they don't understand the code themselves, how are they going to explain to the other people in the company what the code does, and build together? And I don't think anyone has really solved it well at scale. I heard some podcast also with the Anthropic co-working team, and at least the way I remember it was that the podcast asked, hey, how did you make this so good? And they were like, yeah, just everyone on the team coded their own version, and then we picked the best one. And I was like, damn, if that's the best we can do in teamwork, you know, it's kind of, I mean, in a way it's cool because it's like the ensemble method just applied to people, and you know, it's cool. You can explore so much more, but it's also like it does remove all of the teamwork. At that point, it's just everyone working in isolation. You're just duplicating. Yeah. So I'm curious how we're gonna solve that.
It's performance versus competence, and I guess we're kind of making a bet collectively that performance is all that matters. Thomas, it's been amazing having you on the show.
Yeah, it's been so much fun. Thank you, Tim.